Hello, this is Zhengwei, and our paper is Profit, Speeding Up Distributed DNN Training with Predictable Communication Scheduling. As you know, in distributed deep learning, amounts of data will be transferred across devices in each training iteration. And parameter server, a centralized communication architecture, is widely used for data parallelism. However, this architecture has some bottlenecks. The communication will block the computation of workers. To solve this problem, several related works design priority-based communication scheduling strategies. For example, P3 is dedicated to overlapping the backward propagation with the gradient push process to make forward propagations start much earlier. However, these excellent solutions still have existing problems. One problem is that the slow network transmission makes GPUs fail to timely acquire model parameters, and thus the GPU utilization will dramatically decrease to zero between iterations. Another problem is that there exists non-negligible performance overhead. For example, the smaller size of partitions in P3 dramatically decrease the training rate, and the training rate of byte schedule fluctuates rapidly during its hyperparameter auto-tuning. Fortunately, we observe that the communication characteristic of gradient transfer follows a stepwise pattern over time. Such a pattern is due to the communication mechanism of PS architecture in distributed deep learning, so it is independent of DNN frameworks, DNN models, datasets, and hardware architectures. We can thus take advantage of this stepwise pattern to design a better scheduling strategy. So we proposed our Profit. The core idea of Profit is that it predicts the transferred gradient data size by profiling the time interval between blocks and the available network bandwidth during model training. Several recent works, such as P3 and byte scheduler, are very close to our solution. But Profit ensures that each gradient can be transferred by greedily utilizing the network bandwidth resources without blocking the higher priority gradients. In this way, Profit makes the critical gradients be transferred as fast as possible, yet with negligible runtime overhead. To better illustrate our idea, here we show you an example. You can see from this fig that the default MXNet transmits gradients with the default FIFO order. P3 slices the gradients into small partitions to ensure a timely preemption, but as is discussed above, with non-negligible overhead. Byte scheduler uses some hyperparameters to successfully get a trade-off between preemption and runtime overhead. Different from P3 and byte scheduler, our Profit introduces the concept of gradient blocks by identifying the stepwise pattern for DNN training and only transfer the gradients that can be timely transmitted before any higher priority gradient is generated. Such a profiling job is a lightweight one, so it has negligible runtime overhead. Now it's time for modeling. First, we show you the total time of DNN training, which consists of two parts: the time cost for backward and forward propagation, and the idle time of GPU resources during the entire training process. The first part, The time for propagation is considered as a constant value in this formulation, and only the second part is related to the communication scheduling strategy. We can use a better communication scheduling strategy to get a smaller t-weight value, and thus to improve the GPU utilization in distributed deep learning. But what is t-weight? Here we show you the formulation of t-weight, which is the sum of two parts. GPUs must wait if required parameters are not timely transmitted, so we need to sum up all these GPU idle times as the first part of this formulation. Also, GPUs will come from the working state to the idle state when gradient 0 is generated, and come back to the working state when gradient 0 updates its parameter. We also need to add this part to t-weight. Previously, we showed you how TR and t-weight are formulated, and now we want to figure out how to schedule the gradient transfer time to minimize t-weight. We want to make the value of t-weight as smaller as possible, but with several constraints. These constraints are quite obvious. For example, a gradient can only be pushed after it is generated, and we want to avoid too many gradients being transferred together. During the forward propagation, the remaining gradients must be transmitted in the order of priority. To take advantage of the stepwise pattern to find the optimal gradient, we add one more constraint here. This formulation ensures that the gradients will be transferred before any higher priority gradient is generated in the backward propagation. Based on the model, we design our algorithm by leveraging the block time interval and the monitored network bandwidth to determine the start time of gradient transfer during both the backward and forward propagation. And here is the pursuit code of our profit. We use a loop to determine the time of gradient transfer during both the backward and forward propagation. In the backward propagation, we greedily assemble each gradient if it can be transmitted in time, and we assemble them into a gradient block. In forward propagation, gradients are transferred in the order of priority. These behaviors ensure critical gradients can be transferred as fast as possible. We implement this algorithm on the abstraction layer of BytePS, which is designed to support multiple frameworks. Profit consists of 4 modules. Training Job Profiler pre-trains the DNN module to obtain the gradient information. It is a lightweight job, so Profit has negligible runtime overhead. Network bandwidth monitor. It periodically acquires the available network bandwidth. The gradient block assembler will leverage the gradient and network bandwidth information to find the optimal start time of gradient transfer using our algorithm. And the gradient blocks with optimal scheduling time will be sent to the scheduled queue, which will be used by BytePS core to start the DNN training. We evaluate our profit on 8 G3 instances in Amazon EC2. We evaluate our profit using 3 metrics. 1. The model training rate. 2. The GPU utilization and network throughput. And 3. The wait time of each gradient data and start time of the forward propagations. Profit proves to be effective because it can significantly improve the training rate by 10% to 40%, as is shown in the first figure. You can also see from the second and third figures that the GPU utilization and network throughput of Profit are much higher than that of ByteScheduler. Also, Profit significantly reduces both the wait time of gradient transfer and the transfer of gradients. You can see from this fig that Profit only takes 1/3 of the time in communication, which makes it performs better than default MXNet and ByteScheduler. Profit is also robust. It works better than state-of-the-art priority-based communication scheduling strategies under different batch sizes and different bandwidth conditions. In a heterogeneous environment, Profit also slightly improves the training performance compared with ByteScheduler. Here comes a conclusion. We design and implement a predictable communication scheduling strategy named Profit, which leverages our observed stepwise pattern of gradient transfer start time to make the forward propagation start as early as possible. It reduces the waiting time of GPU resources and thus improves the DNN training performance by up to 40%, yet with negligible runtime performance overhead. That's all, and thank you.